Hello! It can sometimes be a bit difficult to know which chapter I should be choosing to put this content in, because it involves logarithms, which is a pure topic, but then also this content has a very strong link to both correlation and regression lines, which is arguably a statistics topic. Therefore, as I'm going to be covering this content across two videos, I'll probably put one of them within the pure section and the other one in the statistics section, so that whichever avenue people decide to go down when trying to search for videos on this topic, they'll be able to find these two videos. Starting today by focusing more on the role that logarithms play within this content. To explain what's going on, let's say we've got the example of having a data set which is made up of coordinates. That's more officially sometimes known as bivariate data. But let's say one of the coordinates in that data set is the point 2, 1, and another point in that data set is the point with coordinates 4, 6. I'm not going to do it here, but if you were to continue this process on of plotting all the data points in your dataset, and those data points conveniently were to line up in a perfect straight line, then finding the equation of that straight line would actually be very easy, because you wouldn't need all the data points in order to do that. To find the equation of a straight line, you only need two pairs of coordinates, so therefore you could go ahead and do that. This wouldn't take very long to calculate, which would be good news, except for the fact there is a lot of data in the real world that doesn't follow a linear relationship, and instead should be modelled by some sort of curve. For instance, for the dataset I was looking at here, I just have to include one extra point for us to be able to see that perhaps the straight line we were looking at before isn't the most appropriate model. And that problem might only become worse if you were to plot even more points from your dataset. But how do we go about finding the equation of the curve that goes through our data points? The problem is there's lots of different types of equations of curves that we can choose from, and therefore that makes it a real big problem because it's quite easy to find an equation of a curve that goes through just two of the points in a data set, but not one that goes through all your data points at the same time. Therefore, if you don't know what specific type of curve your data is following, it'd be very easy to get stuck in a trap where you use two of the data points to find the equation of the curve, and then see the other points don't fit it. Retry with a different type of curve or a different pair of points, and again, find a curve that goes through those points, but then realize that the other points don't go through that same equation. Eventually, through trial and error, you might eventually find the correct type of curve to do the job you need it to do. The only problem is, by doing this, you've now wasted a lot of effort, because for each of these scenarios, you've had to actually go to the entire effort of finding the actual equation of the curve before you're then able to even check if it's the right type of curve to be using. So, if only there was a way we could check what family of curves we should be trying to apply to our data. Well, good news, because there is, and it involves logarithms. By taking logarithms of the individual data points, we can tell what type of equation of a curve should be fitted to our original data by looking at the new relationship formed by applying logarithms to our data. Let's see how that's going to work by first looking at curves of the form y equals a lots of x to the power of n. If you start by taking logs of both sides, that will get us log of y is equal to log of a x to the power of n. As always, if you're doing something to both sides of an equation, you've got to apply that operation or function to that side of the equation as a whole. So that's why the ax to the power of n has all got to go inside that log. As always, for Maths A-level students in England, it's worth mentioning that whenever I just write log, I mean log base 10, but it's worth noting that this would work with any log base as long as you're applying the same log base to both sides of the equation. Continuing on, we could use log laws to rewrite the right-hand side. Because it's x to the power of n, then multiplied by a by the order of operations, if we want to split this stuff up, we're going to have to separate out the a first before we try to do anything with the n, just because the last thing that was applied is the first thing that has to be separated when trying to rearrange stuff. So therefore, we can use the log law that allows us to rewrite this as log of a plus log of x to the power of n. Then we could use another log law to help us rewrite that power of n as a multiplication out the front of the logarithm instead. At this stage you might be wondering, so what? But if I rewrite this stuff in a different order, it might make it a bit easier for us to see what's going on. So we could have log of y is equal to n lots of log of x plus log of a. The reason this is special is it means we've now converted or transformed the original curved relationship back into a linear relationship again, as long as instead of plotting just the original x values and y values as our data points on the graph, we instead choose to plot log of those original x values on the horizontal axis instead, and instead of plotting those y values, we plot the log of the y values on the vertical axis. What that will mean is our data will form a straight line with a gradient of n, and the intercept with the vertical axis would be log of a. I'm not calling it the y-intercept, but it's effectively that role, so let's call it the log y-intercept, if you will, as that's what we've plotted on the vertical axis. Therefore, this is a nice way of being able to check if data is modelled by this family of curves. If you plot log x and log y values instead of the original x and y values, if that data forms a straight line, then you know the original data is of the form y equals a lots of x to the power of n. Whereas if the log x and log y values plotted doesn't form a straight line, then you know this family of curves doesn't apply to it. Okay, on to a second example, and it's going to be a very similar process. And because the process we're doing is part of the work that you need to be able to do, I'd recommend actually pausing the video at this stage and trying to have a go at a similar process, but with this new equation of a curve instead. In 5 seconds, I will start to go through it myself, so you can then check and see if you had the right idea or not. Okay, so let's have a go at applying logarithms to both sides of this curve as well. So we'd get log of y is equal to log of ab to the power of x. It's worth reminding you about the order of the operations there, because on the right hand side, ab to the power of x does mean b to the power of x then times by a, not a times by b then taken to the power of x, because you'd need to use brackets if you wanted to have that particular sequence of operations. Anyway, therefore that means if we want to split up the right hand side using log laws, we again have to separate out the a before we do anything with that power. So we're using this log law here, and then we can use another log law to bring that power of x down out the front of that log. Okay, so hopefully this is where people got to. But once again, I'm going to choose to rewrite this exact same line of working in a different order, just so it makes it a bit easier for us to see what's going on here. So I'm going to rewrite it as log of y is equal to log of b lots of x plus log of a. And the reason this is interesting is because it once again means that we have transformed our curve to a straight line relationship, a linear relationship. But in order to have the linear relationship this time, we're not plotting the values of log of x with log of y, we're plotting the values of x with log of the y values. So the x values are being plotted in their original format, and it's only the y values that we're taking the logarithms of before we plot them. If we do this, that means that this time the gradient of the straight line that we get from doing this will be the value of log of b. And the y-intercept, but again technically it's the log y-intercept, is going to be given by the value of log of a. So in summary, if you want to know what type of curve models your data, then if you plot the values of log of x and log of y and it forms a straight line, then you know the original data is of the form y equals a lots of x to the power of n. Whereas if that doesn't form a straight line, then you know that type of curve isn't suitable. And instead you could also check if the values of x and log of the y values plotted forms a straight line instead, because if that does form a straight line, then you know instead the curve is of the form y equals a lots of b to the power of x. Again, if that wasn't a straight line, then you know that wouldn't be a suitable curve as well. Now, it's worth mentioning that it doesn't hurt to remember these two facts, particularly for those quick 1-mark questions where you'd have to identify what type of curve should be fitted to the data, given that they've already taken logarithms of some parts of the data or all of the data and plotted it and it formed a straight line, etc, etc. However, you do also need to be comfortable doing that logarithm rearranging we were showing just now, because you can get asked to do that in show that or proof questions, so being able to derive why plotting x against log y forms that second curve, etc, etc, is also important too. But to get a sense of accomplishment, to finish off the video, let's go back to that data we started with and decide once and for all what type of curve fits that data. Currently you can see the original data being plotted, but if instead we choose to plot the values of log of x and log of y, then that will cause your data to look like this. If we zoom in and then try to fit a straight line to these three new data points, you'll unfortunately see that it isn't quite forming a straight line relationship still. So therefore, as plotting log of y against log of x has not formed a straight line, therefore we know y equals a lots of x to the power of n is not a suitable equation of a curve for our original data. Whereas if instead we choose to plot the original x values with log of the y values, then the data will look like this instead. If we now try to fit a straight line to these data points, then we can see conveniently they do line up in a linear relationship, and therefore as log of y against x formed a straight line, we know the original data must be forming a curve of the format y equals a lots of b to the power of x. And that will do us for today's video. As already mentioned, there will be a second video which will be covering the links between this stuff and correlation and regression, as well as showing you how to actually find the parameters a and n or a and b in those formats for the equation of the curve once you've realized which type of curve your data is fitting. So hopefully you found this video useful, and I'll see you in a future one. Goodbye!